Okay, so velocity time graphs are often another good tool to analyze the motion of a particle and the determine accelerations and um, distances and things like that. So if we consider what a velocity time graph components are. So if we consider the gradient of that line, velocity over time, that's my acceleration. So the acceleration is the gradient at any point. Okay, and the other interesting one is the area under the curve of velocity time graph gives me the distance and the displacement of the particle. Okay, so the displacement represents the signed area. In other words, we don't have to worry about whether it's positive or negative in terms of above or below the axis. We just integrate, well, we integrate or we add up the areas, because don't forget, I guess, this part of the journey here represents travel to the right in a positive direction. This part of the journey here, okay, negative velocity. So at this point where it crosses the v-axis, the velocity axis, this area here represents traveling back towards the origin, okay, because velocity is now in a negative direction, all right? And so then if you add them together, you find our position at any point in time, our displacement. If we want to know the distance we've traveled, however, we're going to have to work out the total area bound by the graph, but we have to calculate areas above the axis and below the axis separately, otherwise those negative areas will cancel. What's going on? So let's have a look. So a particle starting at 10 meters per second accelerates uniformly for 12 seconds, after which it maintains the velocity for the next 12. So if we just go through the story and have a look. So starts at 10 meters per second, accelerates uniformly for 12. So a uniform acceleration means it's a straight line. Yeah, acceleration is constant for the first 12 seconds. After which it maintains its velocity, so it's constant velocity, so it's a straight line. And then it retards or slows down uniformly back to rest in 8 seconds. So 12-second acceleration, 12-second constant, 8-second deceleration. All right. The particle ends up 800 meters from where we started. So we need to try and find out what that maximum velocity was. So what we do know is that the area under that curve or under that graph is equal to the distance traveled, which in this case is 800. So if we just split the sections up, so you can see in here, I've done it, I guess we could have used a trapezium, which might have been a smidgen quicker, but I've just gone with a rectangle and a triangle. So there's my rectangle there, 10 by 12. The top part of the triangle is a half base height, which is a half times 12 the height, or whatever v minus 10, whatever v is less 10. Okay. If I multiply that, I'll end up with 120 plus 6v minus 60, or 6v plus 60 is my total area. The second part of the journey, okay, is just a rectangle. So area is 12 by v, which is just 12v. Last part of the journey, again, another triangle, a half base height, which is a half times the 8 seconds times the velocity, which was the maximum, which is 4v. So if I add all those up, I should get 800. And for that to be true, the velocity needs to be 33.6 meters per second. Okay? So no doubt that diagram is really quite significant. All right. Velocity of a body is expressed by, find the total distance it travels in the 2 seconds. So it's the total distance. All right? So the total distance is the area under a velocity time graph. So we've got to think about, I guess, the sections of our curve. So first things first, worked out at t equal to 2 that our velocity was actually at 0. So the areas we're looking for, I've got area all over the place. Right. Area there and area there. So I've got to add up those two areas, don't I? Clearly the green area is below the axis. The red area is positive, so that's fine. So the area below the axis between 0 and 1 is 5 on 6 units. The area above the axis in red is 1/6 unit. So the total, so the total distance I've travelled is I add those together, all right? Whereas the displacement, okay, is I'm going to add them together, but without worrying about the negative. So the first part of that journey is actually -5/6, isn't it? Plus 1/6. Probably left off. We should have a -2/3 there. Okay. So it suggests that really our particle is still to the left of our origin, isn't it? Okay. So distance, displacement. Keep in mind in terms of velocity, time graph, how they fit in together. Okay, so a regular in these is our old car travelling. So a motorist needs to travel 50 kilometres. So accelerates uniformly from rest until she reaches 25 metres per second. So uniform acceleration is straight line. Travels at this speed for the whole journey. And last section where she decelerates to a standstill, so she comes to rest. Okay, and the deceleration is the same as the acceleration at the start. She wants to accelerate for 1/100th of the time taken. So maybe the time is t on 100. The slowing down time is t on 100, which means the constant travel time is 98 t on 100, 98 100ths. Again, total area is equal to the 50 kilometres. So area 1, a half base height. Half times the base times the height. I'll go to area 3 because that's the same triangle. So if I add those two together, I'll just get that, 25 t on 100 in reality. Plus 98 t on 100 times 25, which is area 2. And that's got to equal the 50,000 metres, since we're in metres per second in terms of our distance. So if we add these together, we end up with 99 t on 4 equals 50,000. Multiplied by 4, divide by 99. Oh, that should be in minutes there, shouldn't it? We'll end up with 2020 seconds, which is near enough to 33.67 minutes. So a bit over half an hour. Does that seem reasonable? Probably. So to work out the acceleration, it's going to be the rise over run of one of those triangles. So it's going to be the rise of 25 over t on 100. T was 20.2 on 100, and that comes up to be 1.24 metres per second. Okay. Let's keep working through. All right, so now we've got our car chase going on. A motorist is travelling at a constant speed of, let's use that. A motorist is travelling at a constant speed of 120 kilometres per hour. Passes a stationary police car. He then continues that speed for another 15 seconds before decelerating over 5 seconds back to 100. So there's our sitting on 120 still for another 15 seconds, slowing down for 5 seconds, and then continuing our journey at 100 as if nothing's happened. Police car takes off. As soon as he passes us, so there's my police car, the instant he passes, we accelerate over 25 seconds, and we get up to 130, and then we travel at 130 until we catch the car. How long does it take the police to catch the car? All right. So again, it's one of those ones where to catch the car, the distances we travel need to be the same. So we're going to reference time as the time that it's taking the police car to travel. So from the moment it leaves. So what does that mean? So the motorist, for example, the first section, distance travelled in that first 15 seconds is just 120 by 15. So let's just talk about the speed, and we'll talk about what we've done. The little next section is a trapezoid, a half A plus BH. So there's my half A plus BH, the area there. And then we've got this third rectangle, second rectangle, where it's going to be equal to a speed of 100 k's an hour times t minus 20. So what we're sort of saying is, say over here somewhere, so a capital T is when the police car catches up to the motorist, okay? Now, don't forget, all of these speeds have to be converted, if you like, into meters per second, because everything's about seconds in terms of the time. So in reality, this here needs to be multiplied by 5/18. That has to be multiplied by 5/18. This has to be multiplied by 5/18. So what if we just take our 5/18 out the front? Okay, and that way it converts everything to the appropriate units. And if we do the same for the police car, again, the triangle at the start, a half base site, 25 by 130 times 5/18 if you like, to get the 130 into meters per second. Plus, we're sitting at 130 times the area of this rectangle, so the height times the base, which again is t minus 25 in this case, because our police car has been travelling constantly after the first 25 seconds. Again, both of them individually multiplied by 5/18, okay, to get it into the correct units. So if we simplify and group the expressions together, my motorist becomes 100 t plus 350 times 5/18. My police car, 130 t minus 1625 times the 5/18. And now when we equate the two distances, the 5/18 are cancelled. So it keeps our computations a little bit tidier, because I don't have to worry about that 5/18. All right, and so if we transpose and solve for t, I get t is equal to 65.83 seconds. So that's how long it takes me. That's how long it takes a police car to catch up, just a little over a minute. How far has he travelled in that time? To the motorist, how far is the motorist? Well, both of them, it's either one. So the distance for the motorist, 100 times this time that we've been travelling plus 350, which was sort of the rule that we had there, which gave us 1.926 kilometres. All right. Okay, so let's keep moving through. An object travels in a line. Its acceleration decreases uniformly from 0 to -5 meters per second squared in 15 seconds. So let's see. So really what we've got is an acceleration time graph, haven't we? And my acceleration is decreasing uniformly. Okay, so the equation of that line is rise over run, y equals mx plus c. C is obviously 0. The gradient there is 5 over 15, but negative, so it's minus a third. So in actual fact here, we have got a rule for the acceleration, but we had to do a little bit of digging around to get it. Okay, so again, it's just one of those ones where we put the information down and see how it presents itself. So once we've got that, I think it falls out pretty nicely. So we integrate that, we get the velocity is minus 1/6 t squared plus some constant c. T equal to 0, the velocity was 24, so we get a rule for the velocity. The distance travelled at the end of 15 seconds, we put t equal to 15, and we get negative 13.5 meters per second. Distance travelled, area under a velocity time graph, the signed area. So again, we better consider above and below the axis. So there's my 15. So clearly we've got two distinct areas here. So we've got the area, if we do a quick graph sketch, area A, which is obviously going to be positive. Area B, which is clearly going to be negative. So there's my area B here, from 12 to 15. So we put the magnitude around it, and we've got our just integrating. In reality, I just put on the CAS 192 plus 19.5, give me a 211.5 meters. All right. So again, once you've got your equations, we just follow the same processes.